Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for July 24th, 2013.
On today's show, a nanowafer tunes for optimal light absorption, subtle differences in butterfly wings could inspire new materials, paper-thin electronic skin lights up at a touch, and a 16-year-old from Oregon develops a method to help optimize quantum dots for solar applications.
A wafer nano-engineered at Stanford can be optimally tuned for light absorption. With the extremely thin material's ability to absorb nearly 100% of incident light of a specific wavelength, it is the thinnest, most efficient visible light absorber to date. Complete absorption of visible light using a minimal amount of material is highly desirable for many applications, including solar energy conversion. Because they require less material, thinner solar cells cost less. The challenge lies in reducing the thickness of the cell without compromising its ability to absorb and convert sunlight. An ideal solar cell would absorb the entire visible spectrum as well as the ultraviolet and infrared. The Stanford team found they could tune a surface containing billions of gold nanodots to absorb 99% of the reddish-orange light at the 600 nanometer wavelength. Their nanowafers result in solar cell absorbers that are about 1,000 times thinner than those commercially available. Using atomic layer deposition to place a thin film coating on the wafers allowed the system to be tuned by simply changing the thickness of the coating around the nanodots. The next step is to demonstrate that the technology can be used in actual solar cells. The results were published in Nano Letters.
Subtle differences in the small crystal structures responsible for the varied color patterns in butterfly wings could lead to new material coatings that change color by design. Butterfly wings can do remarkable things with light, but much research still needs to be done for humans to replicate the wing's light-manipulating properties. 3 tropical butterflies under investigation all display iridescence, with different colors from bluish green to yellowish green to deep green, but all 3 shift toward deep blue when viewed from a sharp angle. Researchers at Hong Kong Baptist University discovered that the wings contain specialized architectures similar to a Bragg reflector. Light reflected from the wing was measured using angle-resolved reflection spectroscopy, revealing that the varying colors of the 3 species' wings arise from slight differences in crystal parameters. Information from these wings could lead to designer materials that wouldn't need to be painted or dyed one specific color. The same article of clothing, for example, could reflect a subdued color for the day and a more ostentatious one for evening. The researchers are now investigating the color-generating mechanisms of other insects, including the metallic effect produced by iridescent beetle shells. The study was published in Optical Materials Express.
A new milestone by engineers at UC Berkeley could literally help robots become more touchy-feely. A team led by Ali Javi has created the first user-interactive sensor network on flexible plastic. The new electronic skin, or E-skin, responds to touch by instantly lighting up. The more intense the pressure, the brighter the light it emits. Integrating sensors into a network is not new, but converting the data obtained into something interactive is the breakthrough, they said. The latest experimental samples of the E-skin measure 16 by 16 pixels. Within each pixel sits a transistor, an organic LED, and a pressure sensor. In addition to giving robots a finer sense of touch, the engineers believe the technology could also be used to create wallpapers that double as touchscreen displays, or could be laminated to a dashboard to let drivers adjust electronic controls by gesture. The lab is now engineering the sensors to respond to temperature and light as well as pressure. The work is described in Nature Materials.
Last week, we featured 15-year-old Anne Makasinski of British Columbia demonstrating the flashlight she developed that's powered solely by body heat, a project that earned her a place in the top 15 of Google Science Fair this year.
This week, we wanted to mention another top 15 finalist, Valerie Ding of Portland, Oregon. Her project demonstrates a method that will enable rapid optimization of quantum dots for solar applications. Good luck to both girls as they head to Google headquarters in Mountain View, California in September.
Well, that's it for this edition of Light Matters, the Photonics Industry's only weekly newscast.
As always, you can write to us with your questions or comments at lightmatters@photonics.com, or like the erudite polymath, you can comment on YouTube.
Or you can write a review on iTunes. Thanks for watching, and we'll see you next week.